So let's start off real quick with a quick introduction from our side. I'm Niels Hagoort. I'm from the Netherlands, as is Frank. I'm a freelance architect, vExpert, vCDX. And you can find me on Twitter and on my personal blog. Frank, if you will.
Yeah. So, hi everybody. My name is Frank Denneman. I work for VMware, and I focus on VMware Cloud and AWS and resource management. So this talk is about what Niels said about host resources. Now, vSphere does a tremendous job of providing the resources to the virtual machines. But in some cases, you might want to tune vSphere so it provides a little bit better resources. So this talk is more about getting the most out of your vSphere environment. So by general, when you run your VMs without configuring too much, it works good. It works good enough for most. This is just about squeezing out the last bit of performance. So the best user experience is actually not having peaks of performance, it's about consistency. If you have a consistent performance, typically your users will respond better because they will get used to the performance. If you have spikes, you typically also have load times as well. And that's what sometimes makes the user to call you up and say, hey, it doesn't work, or it doesn't perform any more like it used to do. Well, that's actually the default, and the spike was the extra. So by creating a consistent performance, typically your customers will be more happy. Now, how do you get to that point? How do you get consistent performance? And that's typically by removing the moving parts. Now, in a computer, there are not a lot of moving parts, so it's just basically a figure of speech. But in the end, it's basically try to reduce as much as constructs as possible. Now, let's go into that a little bit more deeper. So when we talk about a server, a ESXi host, one of the key elements is always how much CPU and how much memory do you have in a host. So one of the most common configuration is a 20 CPU core system with 512 gigs. Now, what does that look like from a compute perspective? So I draw out a diagram of two physical CPU packages. That's basically the thing you can hold in your hand. That's CPU 0, and the other one is CPU 1. And in that CPU package, that package contains a lot of cores. In this whole presentation, I use the example of 10 cores per CPU. So that means CPU 0 has 10 cores, CPU 1 has 10 cores. Now, each of these CPU packages, they have a memory controller integrated. That means that the memory is directly attached to the CPU itself. So in this case, we have 256 gigs of memory attached to a physical CPU. Because we have two physical CPUs, you have 512 gigs of memory. Please be aware that this is created equally, but there are a lot of systems that don't have that configured identically. So check that out as well in your system. So let's go a little bit deeper. I already said, specified NUMA nodes. Now, oh, it didn't click. There it is. So a NUMA node is, NUMA stands for non-uniform memory access. And that means that the memory access is non-uniform, as it describes. That means that sometimes it's faster, sometimes it's slower. Why is that? That's why, if you connect to your local memory, so if a workload runs on CPU 0, it can connect to the memory that is connected to its memory controller faster, because the path is just shorter. Typically, you get better performance. If the workload that runs on CPU 0 needs to talk to the memory that's connected to the other CPU, that takes a little bit longer because the path is just longer. It's just pure physics, right? In order to do so, there's called the interconnect, and that's basically the key ingredient whether you get consistent performance or not. So the idea for workloads that need consistent performance is to actually try to configure the workload to to confine it in one single CPU. So it can always use the local memory controller. It does not talk to the remote memory, as we call the memory of the CPU on the other side. So why is that? So we did some testing during when we wrote the book, and we noticed that if a workload is running on socket 0 or CPU 0, and it talks to or it communicates to its local memory, you see a speed or latency roughly around 75 nanoseconds. But if it starts to talk to the remote memory, it's still in the same system, it is roughly about 130 nanoseconds. So almost twice as much, right? Now this is from a latency perspective, but there's also the bandwidth that you need to take into account. So with the configuration of CPUs, especially the V3 and the V4 of the Xeon, you have 3 types of QPIs. That's the Quick Path Interlink or Interconnect. That's basically the name for the interconnect itself. And you can configure, or you can buy one that is faster or slower. So if you buy the fastest one, you get 9.6 gigatransfer per second. Now, gigatransfers per second is a difficult number to grasp, so we calculated that in gigabytes. And then you can see that it's 19.2 gigabytes. Now that's one direction. You can communicate both directions. So that means that the bandwidth between those two CPUs is 38.4 gigabytes per second. Now that seems a lot, and it is quite a lot, but that is the theoretical numbers that Intel provides. So we did some testing as well, and we found out that it was actually a little bit lower. So instead of getting 38, you get almost 30. Still a lot. But if you compare that with local memory, and if you use your 4 channels, you get more than twice the amount of bandwidth. So that's the reason why you want to keep it within a NUMA node itself. You get the lowest latency, you get the highest bandwidth. Now this is calculated on a V4 system, so that was the previous model. Today we have Intel Scalable Xeon, that's the latest one, that uses 6 channels. So that means 6 times almost 20 gigs of memory bandwidth, right? So you get even more. Now, if we dig a little bit deeper, you have systems that have 10 cores, or some have 20 cores, or even more. Now, depending on the number of cores you have in a Xeon system, you have what they call low core count, medium core count, and high core count. Now, if you have a medium to high core count, you have actually two rings inside of a CPU. That means with this system, this is the biggest one, there are 2 rings that are used to communicate between the CPUs, the memory controller, and the cache itself. Now the cache is shared amongst all cores. So that means that, do we have a, no, we don't have one. Sorry. So if you have a CPU on the left bottom that states core 0, if that workload is running on that core and it actually needs memory that's located on the other memory controller on the other DIMM, it actually needs to traverse between the rings. That takes time as well. Now for the extreme latency sensitive VMs, you can actually divide up this CPU with as 2 NUMA nodes by using a cache snoop setting inside the BIOS. We described this in the book thoroughly. This is what we call cluster on die. That means you have one CPU package in your hand, but every ring will become a NUMA node. right? So that allows you to actually confine the workload even further inside the CPU to only use one part of the CPU. Again, this is for the extreme low latency sensitive workloads. So we're talking about stuff like high frequency trading, that type of stuff. Now I talked a little bit about how the hardware actually works, but there's also the VM kernel. Now, the VM kernel has something that is really smart that's called action affinity. And that actually is built on the last diagram that I showed. So with action affinity, what we do is that when two VMs run on the same host and they communicate with each other on a regular basis, we know that they share memory. Now, because they share memory, they have to go through all these cache layers. So the light gray ones are the cache slices within the system. So what we want to do is we want to make sure that all these cache slices are close to the workload, or actually the workloads are close to the slices as well. Now this is on one CPU, but we have VMs that are running on two CPUs in the same system. Now to enhance that communication, what the ESX kernel does is it starts to schedule them together on one physical host. Oh, sorry, on one physical CPU. So in this screenshot, you will see that I've got two VMs, and one runs on home node 0, which is the first CPU, and one VM runs on home node 1. So you see that there's an equal balance of vCPUs per physical CPU. So this feels balanced. But the reality is that these two VMs, they communicate on a really regular basis, almost instantly, almost continuously. So this is something that the VM kernel detects. What happens, the VM kernel starts to pile those two together on one physical CPU. Now, if you look at your ESX top, you notice that, hey, I've got all my 8 CPUs running on one NUMA node, while the other one is empty. That doesn't make sense. Well, from a peanut butter spread perspective, yeah, that doesn't make sense. But from a workload perspective and on a low-level workload, that does make sense. So please be careful when you see this. You think, hey, it's not working. Typically, this is because two VMs are communicating with each other on a very regular basis. Now, if you don't want that, and if you say, I'm smarter than the CPU scheduler, we have an advanced setting. And this is called NUMA locality weight action affinity. It's by default set to 130. Don't ask me why it's 130. But if you want to disable it, set it to 0. That's basically, you basically disabled that advanced intelligence, right? So in the VM kernel, we have actually two CPU schedulers. We have what we call the CPU scheduler itself and the NUMA scheduler. Now the NUMA scheduler is more an advanced option or an advanced scheduling algorithm. It doesn't actually schedule the vCPU on the physical CPU, because that's the responsibility of the CPU kernel itself, or CPU scheduler itself. So I made this diagram, and hopefully everybody can read it. There's a little bit, there's a tiny font. But on the top, you see a vCPU. And if you configure a VM on a default basis, you will always get one vCPU per socket. Now, this CPU socket is interesting and is leading for the NUMA scheduler. And I will show you later on. So on the left side, you see one CPU, one vSocket. Now the NUMA scheduler creates one NUMA client, and that will be the load balancing element for the NUMA scheduler to actually figure out where to place it on the system itself. The CPU scheduler takes that NUMA client and takes the CPUs inside that NUMA client, and it actually configures it and schedules it on the physical CPU. Now we like to call that the pCPU. That's the element inside the CPU scheduler itself. So the P does not stand for physical, what most people think. But we had to call it a name. We had to give it a name. Now that pCPU can actually run on a hyperthread, or on, and that means a logical processor, or on a physical core itself. So the pCPU does not always mean that it runs on a full core. It can actually run on a logical processor as well. That means that there is a performance difference, right? So in general, if you use a hyperthread, you don't get to use the entire core itself. So you don't get to use the cache, you don't get to use all the intelligence. And that's the reason why the vCPU will get more time on the CPU itself. So this is something we call a discount. So if it runs on a logical processor, it is charged 62.5% of the time, and a vCPU that runs on a physical core gets 100% of the time. Now that means if it's entitled for 100%, it needs to run again, right? So that means it is scheduled twice. It will get the same amount of processor time, but it's over a longer period of time. So take that into account if you run really physical or really latency sensitive systems, right? For those systems, some actually recommend to disable hyperthreads. I typically say no, don't enable hyperthreads, but keep your consolidation ratio low, meaning that you start to count your physical CPUs against your virtual CPUs against your physical CPUs, right? So let's dig into the elements a little bit better. So one of the things is called white VMs or virtual NUMA. By show of hands, who have heard of virtual NUMA? Okay. So one of the myths of virtual NUMA is that it says if you are above 8 CPUs, you will get a virtual NUMA system. This is not entirely true. Yes, you have to go above 8, but the next step is it has to actually exceed the number of physical cores of the CPU. So what I've done in this system, I've actually created a 10 vCPU virtual machine, and I deployed it on a system that has 10 physical cores. As you can see at the bottom, it actually states one virtual node, and one virtual node means one NUMA node. It has more than 8 vCPUs, yet it still doesn't go beyond 2 NUMA nodes. Why? It does not exceed the physical core count. So once I start to increase that, and you can see at the top, you see number of vCPUs 16. Now you see at the bottom 2 virtual nodes, right? So now it's going to span because those 16 don't fit in one single physical box. So what the NUMA scheduler does, it actually starts to break up evenly. It distributes the vCPUs evenly. So 8 on one physical CPU, 8 on the other physical CPU. So from a diagram perspective, it looks like this. So you get all your CPUs, your 8 CPUs with your vSockets. It creates one virtual NUMA node, that's the virtual proximity domain, and it starts to schedule it on the physical proximity domain, and that includes 10 physical cores. So it can actually, it provides the CPU scheduler the chance to run those 8s on those 10. So it can actually start to choose whether to run it. On the other side, again, 8 more, same deal. Now I already talked about the default, and that is one virtual socket per vCPU, but some like to change that. So one of the most common situations I see in the US is that people or that customers use 2 virtual CPUs per socket. If you do that, you will create a NUMA node per socket configuration. So now it needs to, the NUMA schedule needs to create 4 NUMA nodes, and it needs to schedule them on the system itself, on the physical CPU package. Typically, you will say more fine-grained allows me to get a better load balance. This is not the case because in the end, it's still the same amount of CPU that it needs to schedule. Now there's another problem with this, and that's actually how we translate this back to the guest OS. And I think that's the most important, because that's the idea of virtual NUMA. We allow the guest OS or the application to understand how the physical environment really looks like, right? So when we have a system that uses 2 vCPUs per socket, we're creating multiple NUMA nodes, and that's something the guest OS sees. So I'm using MS Core Info inside a Windows 2012 system, I believe, 2016 system. And then you see on the top, you see the physical CPUs. At the bottom, you will see the NUMA nodes. So the reality is that it's the CPU or the CPU scheduler inside the guest OS or the application itself. It starts to optimize for this situation. Well, in reality, this doesn't exist, right? Now, with every physical NUMA node, that's how the guest OS sees it, it starts to do some cache optimizations. And that is the problem, because it is all one big cache. So how do you solve that? This is basically over-optimizing, which actually provides a less performing system. So the idea is, if you use vSockets, please figure out and please use the physical environment. So if you know that there are 10 cores, right? Say, okay, I want to have a vSocket. How many sockets or how many vCPUs will fit inside a NUMA node? 8. I will create a system, a VM, with 8 VMs or 8 vCPUs per socket. If you do this, you will get the same way of scheduling on the kernel, but when you look at the cache configuration of the guest OS, you will see that it understands that it's actually using the same cache. So it can better optimize its caching routines for the application itself. This will provide you a way better performance than doing an arbitrary number for your vSocket systems. Now, some workloads are memory intensive, yet they still need to have a lot of CPUs, maybe due to the fact that the software vendor needs to have it or request it. So how do you deal with that? So one of the things what you can do is you can use Prefer HT. And what Prefer HT does, it actually counts logical processes instead of physical ones. So you have 10 cores, but you have 20 logical processes. So that means that the NUMA client can actually go up to 20. And I show this in the screenshot. This is on a 10-core CPU, but because it has hyperthreading enabled, it can now actually run VMs on the same NUMA node. So node 0 has a VM running with 60 vCPUs. So it allows to combine them inside a NUMA node. This is typically done when you have a memory-intensive system instead of a CPU-intensive system. Now, what if you have a configuration that's actually the opposite? So you have a system that actually can be scheduled with the CPUs on the physical node itself, but the memory footprint is larger than the NUMA node, than the physical NUMA node itself. So I created a diagram as well. Now you can see that this CPU has this VM has 8 vCPUs, but it has 96 gigs of memory configured. If the NUMA node has 64 gigs of physical memory, it needs to allocate the memory on the remote. What the NUMA scheduler does, it only looks at the vCPU count. So it will say 8 fits into one physical box. I will try to schedule it there. So in the most optimal way, in a most optimal option, you have 64 gigs local and you have 32 remote. That doesn't always work when you have a multi-vCPU system. So one of the things that you can do in this situation is to actually disable NUMA Consolidate. That allows the NUMA scheduler to actually start to divide up those vCPUs into 2 NUMA nodes. In that case, you will get a better balance. This is not always guaranteed, but it allows you to optimize a little bit better. This is something you should test in your lab first before you start to use this in your production environment. That's the reason why it's an advanced setting. We typically don't want you to use it by default. Now that's a lot of information about CPU and about memory, but we also want to talk about storage, right? So I know it's a long day already, but this is just a question. So shout out if you have an idea. How many CPU cycles does it actually cost to do actually one I/O in the kernel? Any idea? I'm going to call out names now. Sorry?
Millions.
Millions. Well, that's a little bit too much for one I/O, but you're getting close. Luke, do you know?
5,000-10,000.
Okay. Zeffie? Okay. Okay. So the actual answer is 27,000 CPU cycles. So one thing that I always hear from the community is, I want to run 1,000,000 IOPS in my home lab. Well, have fun with that, because it takes 27 billion CPU cycles. Now that sounds like a lot, but you actually have a lot in your system. In a normal 10-core system running at 2.2 gigahertz, you have per CPU 2.2 billion cycles. That means, when you calculate it fast, you need 13 cores to actually run 1,000,000 IOs. Now, you might say, but there's no system actually out there that can run 1,000,000 IOs. Yes, there is. So this Samsung, this is an NVMe device. You can basically, it's local storage, put it in, and it will provide you 1,000,000 IOPS, right? If you run the right block size, of course, but it can do it, right? Now, the interesting thing is, and that's basically the whole idea about reducing the number of moving parts in your system, is that there's also moving parts, or there's also layers of software. This is something that the industry recognized and said, let's change this. If we look at the traditional stack, it has a lot of layers, and every layer is a little bit of latency, and every layer needs to have some of the CPU cycles. So why don't we take an effort and to reduce the number of layers? So this is something what they call NVMe. And NVMe actually, by the reduction of the stack, it reduces the number of CPU cycles necessary for an I/O. So with a NVMe device, one I/O actually takes 9,100 CPU cycles. So 1,000,000 I/O cycles will actually take up 4 cores. That means by changing your software, you actually saved over 9 cores in your system to actually do other stuff, to actually run workload. That's an interesting thing to do. So I looked up the stack, and basically it's like this. On the right side you have this is a SAS stack, which is almost the same as a traditional stack. And on the left side you have the NVMe stack. You will see that there's a lot of layers missing, and that's the reason why it's faster and it's more cost efficient. Now they're now figuring out new stuff and new mediums. And maybe you heard about Intel Optane or 3D Crosspoint. They actually looked at the way to actually reduce even more CPU cycles and reduce the latency by changing the physical elements, but also the software again. So what you see here is the stack, the software stack. And what they mean with future NVMe, that's actually already out, that's Intel Optane. You see that the number of layers take less performance, or take less performance hit. Due to the new configuration, that's true?
Yeah.
Jesus, sorry. Due to the configuration, you can actually get better performance at a lower I/O, outstanding I/O number. So that means that at a Q depth of 8, you actually get already the top performance, whereas a normal flash device, you have that at 32 or 64 or 128. So when you combine those elements, you can start to think about using Intel Optane for your caching tier in your, for example, your vSphere environment, and use normal flash for your capacity tier. because the caching tier can make use of a lower queue depth, right? Doesn't always get bounded that much. So by that, I will give over to Niels for a short time for network.
Oh well, I'll manage.
Okay.
So everybody's still sharpish? It was a lot of information, right? All crammed together in like 30 minutes. So we're going to go ahead and talk some stuff about from a network point of view. And an interesting thing is the trade-off is always being made, right? We are talking CPU utilization versus latency. And nobody likes latency. It's what your users experience as an application or a workload being laggy, being slow. But truth is, we all accept latency, from a network perspective, that is. So we have some features and some mechanisms within the ESXi host that actually allows for CPU savings. And the question you should ask yourself is whether you are tuning your ESXi cluster or host for latency-sensitive applications. For example, NFV workloads, network functions virtualization, and you see a lot of traction gaining in that area by telecom operators, high-frequency traders, everything involved in networking. And you have your typical IT workloads. Those are the workloads that will benefit more from CPU savings and have a higher consolidation ratio, more VMs per host. So we will start off by looking into the CPU savings stuff, right? We have several features which are, every modern NIC supports them. It's like interrupt coalescing, interrupt throttling, buffer, ring buffers. And this is what actually happens within an ESXi host when packets are received, network packets are received on the physical NIC. Those packets are being buffered up to a certain point, and then an interrupt will be generated, and that's actually a hardware or a software interrupt which signals the CPU to process those packets. And because we are processing multiple packets at once, that allows for CPU saving, because less cycles are actually required to process the packets. So interrupt coalescing is one of those features. And this is actually a ESXCLI commandlet, which will allow you to get some insights on what is actually happening on your ESXi host. So what we see here, we see the number of microseconds. And again, we're talking microseconds, right? It's tuning for the most optimum latency. So 62 microseconds are being used to actually fill up a buffer before it's processed. And we can even look a little bit further. Oh, there we go. With the VSI shell. And let me stress out that VSI shell is a source of information. It's insane, but it is not supported by VMware. So it's accessible if you have root access to your ESXi host, but be very careful with it. But for now, we want to emphasize some information which we noticed popped up in the VSI shell. And that is actually that we have a queue depth, and this is a commandlet that shows the interrupt coalescing settings, that we have a queue depth of 64. And the lower highlight is actually the maximum queue length, which is again 64. So if we have 64 packets, then the interrupt will be triggered. Another interesting one is ring buffers. Again, we have a ESXCLI commandlet in which we can see what is actually used for receiving packets for our ring buffers. Now, ring buffers are primarily used, and again, those are enabled by default in every guest OS, but even in your physical NIC. And they're primarily used when a large burst of packets is received by ESXi host, by the physical NIC. Now, it handles, it's kind of in between the interrupt coalescing and the actual VM that is receiving the network packet. And it processes the transportation of those processed packets up to the guest VM, to the guest OS within the VM. But an interesting thing about ring buffers is when you are exceeding the ring buffers, right? That will drop packets may occur. And again, this is for a VM which is sending out and receiving a lot of network I/O. But the thing is, if we look at ESXstop, and I think everybody is familiar with ESXstop, again, a beautiful source for information. And you have, in your network view, actually a drop packet, Rx percentage-based value. And while we were testing, we actually saw a value of 0. So it looked like we were all good. And we were stressing the VM with network I/O a lot. Again, we dug into the VSI shell to actually find out that the buffer is this amount, the 11, almost 1,200 times that the first ring buffer is actually full. So we are exceeding the ring buffer. That leads to packets being dropped, not according to ESXstop, but that's an average, a percentage-based value, right? So with even another commandlet, we noticed that we indeed are experiencing dropped packets. And that's an interesting one because, yeah, well, ESXstop just told us nothing was going on, and on the background there is a lot going on. Luckily, we do have ways to increase, to tune the ring buffers, and that's actually done in the guest OS, and that setting is adhered in the ESXi kernel. And this knowledge base article actually states how it's done, how to increase the ring buffers. So, moving on to the latency part. So all these features we just discussed are all there to create interrupts, to allow your environment, your ESXiOS, to save on CPU cycles, right? If we want to have the lowest possible latency for our VM, then we quickly came to a Polmo driver model. So typically, by default, you have an interrupt-based model. And Polmo driver, as it actually is called, is something that allows the ESXi host to, when a packet comes into a host, it's not buffered, it's immediately processed. So we can do so by using, for instance, the Intel DPTK framework. So that is actually a driver that is running in a guest VM, in a VM, in a guest OS, a Linux OS. And what it does is that it actually interacts with the virtual network adapter all the way to the kernel, you'll need to assign certain vCPUs within your VM that are used for actual polling queues. So if a VM is coming into the system, it is immediately found by the Polmo driver and immediately processed. The thing is, if you the vCPUs you entitle the DPTK Polmo driver to, those vCPUs are consumed like up to 100%. So it's a very CPU intensive way of packet processing. So bringing that back together, this is just to show you what is going on when you are using CPU utilization enhancements, like by default the interrupt coalescing features. So you'll have a lower CPU utilization, but at the cost of latency. So you have a slightly higher latency. And for your typical workloads, that's perfectly fine. Again, if you are going to look at NFV platforms, high frequency traders, they don't mind so much about the consolidation ratios. They are willing to sacrifice CPU time, CPU utilization, to get as low as possible latency, right? So another aspect of getting the best performance for your VM, for your network-intensive VM, we can also look at a little bit more about the virtual machine networking, right? So the virtual machine adapters you assign to your VM. And what we used to do when we wanted to go for the highest performance, the highest bandwidth, the lowest latency, is to have a direct access model to the physical NIC. So the VM is directly talking to the physical NIC. Now, SRIOV is one of those features that allows you to do so. The same with direct access, direct path I/O, sorry. And what it does is actually, you'll have a physical NIC, which supports SRIOV, and on that physical NIC, the physical function, they call it, you'll create multiple virtual functions. And those virtual functions are actually connected to a network adapter in the VM. So you still have a way of sharing a physical NIC, but at the cost of vSphere features that are not usable with SRIOV. So yeah, you don't see a lot of adoption for SRIOV because you'll not be able to, out of my head, to use vSphere HA, high availability, vMotion even. And the thing is, we tested, we were experiencing, we were looking at ways why you want to use SRIOV, because nowadays we have the VMMax Net3 driver, right? And that is widely adopted because it's the most tunable virtual driver. And when you look at the performance statistics, you'll actually see that there is not a lot of difference between the VMMax Net3 and SRIOV. And you'll see a CPU utilization in the graph and the actual throughput, right? So the emulated parts, the E1000E, which is by default shipped if you spin up a Windows 2000 or Windows 2012, 2016 server. But still, VMMax Net3 looks like the virtual adapter to go with. Now, if you even want to take it a little bit further, we luckily have some innovation going on within vSphere that allows you to directly talk to memory. And that is where it's getting interesting, right? So this is a new feature, which was released with the 6.5 release of ESXi. And it's the virtual remote direct memory access, virtual RDMA. And that is an interesting one. There are still a lot of limitations. I believe you still can only have one virtual RDMA device in a VM. But still, what it does, you'll see a traditional stack on the left side. There you have your application buffers, the whole TCP stack, all the way down to the device driver and your physical NIC. And sort of the same goes for the virtual RDMA driver, with the big difference that once the control path is set up and the data is starting to flow between multiple VMs, then the whole kernel is bypassed. So you talk directly to your host channel adapter, which is, well, sort of the same as a physical NIC. And then you can use high-speed transport networks, right? We have InfiniBand, we have iWarp, and nowadays, from a vSphere perspective, only RDMA over converged Ethernet is supported, but we will probably see some adoption for other high transport networks as well. And that is interesting, can be an interesting use case, because you are now able to directly communicate between multiple VMs, multiple ESXi hosts, from memory to memory over that high transport network. One interesting use case we saw, and there was actually a whole session about it, was about vMotion. And vMotion that was able to leverage the virtual RDME spectrum, which allows for amazingly fast vMotions. So be sure to look that one up in the catalog that is online. And on that note, we still have 4 seconds. Nice. So I want to close off with our book. All the stuff we talked about today is actually all combined in one book.